So welcome to everyone. Sorry for the delay. We're just 2 minutes, 5 minutes more of delay. So just I live here with Ricardo.
Okay, hi everyone. As it was for yesterday, please let me know if I write too small or if you don't hear me, and write it in the chat so that people who are connected here can tell me. And we start in 2 minutes.
So welcome to everyone for the second lecture. I hope the frame is okay. So we're happy to have Ricardo for this second wonderful lecture, I'm sure. So Ricardo, please.
Okay. We close the door. Okay, so last time I did not finish what I wanted to do. Just a brief recap. We are talking about Turing instability for reaction diffusion systems. We studied the simple case of 1D domain with periodic boundary conditions. The equations, we have two substances who react and diffuse in this domain. They are U and V. And so we have the partial derivative of U over time is equal to a nonlinear function of the reaction between U and V. And then we have the diffusion, so the Laplacian, which is simply the second partial derivative with respect to space because it's a 1D domain. And then the same for V. And we solve the system. So we have a homogeneous equilibrium. And then we impose that this equilibrium is stable. And so we have the conditions on the Jacobian of the linearized systems. So the derivatives of the functions with respect to the concentration computed in the fixed point. So I'm going quick because this is just a recap of last time. And so we had the first two conditions. This matrix is stable if the trace is negative and the determinant is positive. And so we have the trace. So Fu plus GV negative, and then the determinant Fu times GV minus GU FV positive. Then what we did was to perturb this equilibrium. So to activate the diffusion, and then we solve the system in the Fourier space. And we have to impose that this new system is unstable. And so by doing that, we obtain two other conditions, which are the first one that involve also the diffusion coefficient. So here we have the local stability of the homogeneous system. So we don't have the diffusive part, but now once we perturb the equilibrium with an inhomogeneous perturbation, we activate diffusion. So in the new conditions, the reaction and diffusion pairs are mixed. And so we have DUGV plus DVFU bigger than 0. And then we have the fourth condition that is a bit longer to write, but you can find it in the other video, and then also in the notes that I will give you, and in the papers that are on the Dropbox. So the last thing I wanted to do regarding the Turing continuous support was to prove the claim that I made at the beginning, that the new interpretation in the 70s of Geard and Meinhardt, that the activator has to diffuse slower than the inhibitor to have Turing patterns. So we can prove that these conditions, so 1, 2, 3, and 4, the conditions imply that the diffusion coefficient of species B, the inhibitor, is greater than the activator. So the first one tells us, so we have FU plus GV less than 0. But then from the third one, we also have that at least one of them needs to be positive, because we have diffusion coefficients who are positive definite, so they cannot change the sign. Okay, so well, I wrote this one. 1 plus 3 tells us that FU times GV is negative, so they don't have the same sign. We say that FU is positive because it's the activator of the system, and so that GV is negative, is the inhibitor. So I will delete the conditions, assuming that I will not need them. I need only the third one, so I will keep the third one and delete the others. So from the third one, okay, no, so we arrived to this, but then condition 1, since this is negative, it means that FU is less than the absolute value of GV. So this to be negative, we need the negative one to be greater in absolute value than the positive one. Okay. So then from the third, we have that dV times FU is greater than du absolute value of GB. Okay, but then since we have this relation, we have that this is greater than du FU. And so we have that the ratio between the two diffusion coefficients is greater than 1. So that the inhibitor has to diffuse faster than the activator. And so yeah, this is proved. Attention that conditions 1 through 4 are necessary and sufficient to have Turing instability. This condition is only necessary. So we have that the conditions implicate this relation, but vice versa is not true. if we visualize the dispersion relation, that I showed you last time, we will see plenty of those during this mini course. So to have this case, so to have a range of k such that the maximum of the eigenvalue of the Jacobian with space is positive, this implies this relation. But then we have many cases. Well, if we have this relation, we might have this. So we don't have instability. And then we will see, hopefully today, that on network, the conditions are not even necessary and sufficient. We need something else. Okay, so I will delete. I said that this was the last thing on continuum support. I lied. There is one more thing that I want to do. To actually have a model. So this model is called Brussellator. It's a portmanteau between Brussels and oscillator. It's a model developed by Ilya Prigogine, who was a chemist at ULB in Brussels. He also won the Nobel Prize. Are necessary and sufficient on continuum support. And he made this model in 1967. So Prigogine. He also wrote some nice books about self-organization, like popular science books. Then the version that we use of the Brussellator is due to Galla and collaborators at Manchester in a paper of 2008. At the end, it's the same model, but it's just a different scaling of the parameters. Okay, so the model is about an autocatalytic reaction, describes an autocatalytic reaction, and we have 4 variables. And those are the reactions. So we have that X, I never remembered them, becomes X plus U with rates A. Then U plus Y with rate B becomes V plus Y. And then 2U plus V with rate C becomes 3U, and then U degrades with rate D. So we consider the evolution of U in time and D and D. We don't have diffusion. Now, this is a well-mixed environment, so it's a special system. We have the form now. We give the form for F U D that we had in the NGUD. That's the model. So when we change model, we can study the Fitsum-Nagumo, Stewart-Landau, Mimura-Marray. There are many models. We change the form in the reaction diffusion equation. We change the reaction part. The domain acts on the diffusion. So if we change support or network, we change the diffusion when the model is in the reaction. And now this is a kinetic model, but Turing instability is broader, works also for systems that are non-kinetics, like the Fitsum-Nagumo that is inspired from neuroscience. Okay, so U is created with rates A. So here we have A, X, and then it's degraded from this. So we have minus B U Y. and then it's created from this reaction. So we have plus C U squared V, and then it's degraded with rate D. So minus D U. And then V is created with rate B. So we have B U squared B. Okay, you already see that there are too many variables. If we want to have a simple system that we can control, we can study in the phase space, we need two species. So for why they do it, we take X equal 1, Y equal 1, and then also the reaction rates A and D equal 1. And so we have the model now becomes simpler. It's 1 minus B plus 1 U plus C U squared V, and then G V is B U minus C U squared V. And this is the model that you will find in most of the papers that are in the Dropbox, because it's the one that not only our group, but many people working on Turing instability use.
What's the meaning of X and Y again?
Variables, so those are, I don't want to say something too specific that then we stay on the internet forever. Species, but then and you depending on the chemistry behind it, what you want to study, you can decide, okay, let's not consider these species, because in your reaction you just add them, and so you can consider their concentration as constant, and so you forget about it. Then you scale it to 1 because it's just simpler. And the same for the rates. So in the formulation made by the group of Manchester, these two equations are the more the one they focus on, and so they get to this. This model.
Like X and Y equal to 0. I mean, this represents something significant as well. Normalize it to 1.
No, but it's not. I think that this means that this reservoir is keep feeding.
Yeah, you can consider like that you have infinite of these, so the concentration doesn't change, and you are interested in the degradation or production of U and D, but that's just an approximation. So yeah, at the end, most of the papers just say, okay, let's take the Russell later, and they start with this, or let's take the Fitsu-Nagumo. But I just wanted to show, since I talked to you about the law of mass action, how actually you get this. And also in population dynamics, you have this kind of equation. I don't know if you've ever seen it in some biomathematical course. So that's why I wanted to show you this, because you you have the concentration evolving is proportional to the degradation or creation is proportional to the concentration of a certain species with a certain rate. So that's the important thing. Now I can delete all these. I just leave the part on the right. Let's study this model without space. So I will not do all the calculations, but I don't know if professor, if there are homeworks for them, but as homework you can check this. So that the fixed point U and V is 1 and B over C. And then the first two conditions for the stability of the homogeneous, the Jacobian is B minus 1 minus B, and then C minus C. This is the, if you take the derivative of the function with respect to the concentration and then compute it in the fixed points. And so the first two conditions for homogeneous equilibrium, they are C greater than B minus 1, and then C greater than 0. This is always satisfied because we are talking about reaction rate. So that's what C and B they represent. And this condition, if we plot in the space of the reaction rate, B and C, it's a curve like this. So above here, we have a homogeneous fixed point. Below, the point becomes unstable. That was one of the things I wanted to talk to you about, but I will not. Here we have a Hopf bifurcation. The fixed point becomes unstable, and the system has a limit cycle, an attractive, stable limit cycle appears. And if you want to know how it works, there are the videos of Timoteo Carletti of last year, and he does formally all the calculations to have it shows how the fixed point becomes unstable, and then you have a limit cycle. So we will ignore this. There is a folder about Hopf instability in the Dropbox. I will tell you probably the last day. So we are here. And then conditions 3 and 2 and 4, once we add space, and this you can check it yourself. They have there are two curves that appear, and at the end, the instability region is something like this. Let's say this triangle. And you will see many of these in the papers that are in the Dropbox and also throughout this course. So this means that we have one first subregion of the space of parameters where the homogeneous state is stable. And here we have a sub-region where if you perturb the system with an inhomogeneous perturbation, you have Turing patterns. This curve here, which, I did it to, it doesn't have a slope greater than 1. Sorry. Changes with the rate of coefficients. So the greater is V compared to U, and the larger the region is. So this is fixed because this is a system without space. So this is fixed. But then with the diffusion rate, this curve changes. And when the ratio is 1, this curve never crosses the bifurcation curve. So you cannot have Turing instability. And I like the brackellator respect to other models because the region is really so clear. If the Fitsu-Nagumo has not such a nice region to visualize, then of course on network it makes more sense to study a model inspired by neuroscience than a chemical reaction. But then at the end, all models are wrong but some are useful. So don't pretend to actually describe accurately the phenomena, but more to discover the mechanisms behind. Okay. Yeah.
Shouldn't the bottom left element that would be minus b?
Yes, thank you. Thank you very much.
Sure.
Yeah. No, sorry. This is C. This is minus b. Yeah. Thank you very much. So this is the right Jacobian. Thank you for that. Okay. So this concludes the part on continuum support. Can I delete everything? Now, let's go with the networks. Remember the triangle? So yeah.
This region that you draw, that region.
Yeah.
And you said that if you do a Martin's perturbation, then there's three patterns.
Yeah.
Like the shape of the region is not really well defined in general, but will it always be from infinite? But necessarily will it be, I don't know, can we have a sort of model in which this region is bounded somehow?
That's a good question. I think so the Brasolator is infinite, and also the Gisborne-Landau, even though it's not really Turing instability, it's called more Benjamin Fair. It's similar concept. I think the Fitsu-Nagumo one is bounded. So I don't see a reason why it should be infinite, but I'm not sure. But then I will. Can you remind me this question after? So I will actually check it out. I forgot my pen. So before starting with diffusion on networks, that is the important part, just some basics definition. So when we talk about a network, we talk about a set of vertices or nodes. Usually graph theorists call them vertices. In network theory, they are nodes. And edges or links. Again, graph theorists, they call them edges, and we call them links. But then we always borrow the notation from graph theory. And so let's say we have E and J who are nodes, and we have that there's a link between I and J. So I and J is in the set of links if I is connected to J, and this is the adjacency relation, and it's commutative if the network is symmetric. And so we can fully represent a network by its adjacency matrix, whose elements are 1 if I and J are connected, and 0 otherwise. And then, of course, doesn't have to be 1. It can be any positive real numbers. In some applications, they're also negative. I have no idea what it means. So in my world, it's always positive. And so just making an example, I don't know, have you ever seen the adjacency matrix, how it is built from? Okay, then let's take a toy network. So node 1, 2, I don't know why I call this 5 in my notes, 4, and 3. And then I connected this, and this. Okay. So A is going to be a 5 times 5 matrix. And so the form will be, let's see if it fits here. Usually we take the convention that a node is not connected to itself. but that depends also on the application. Sometimes there is it's this that's called, I think, there is a name for graphs with self loops. I don't remember. Multigraphs, if there's a link, like there are multiple links between two nodes. So one is connected to 2. It's not connected to 3. It's connected to 4 and not to 5. And then we proceed analogous way. So 2 is connected to 1, not to itself, so to 3, not to 4, and to 5. 3 is connected not to 1. Matrix. And so it has the dimensions of the nodes. So 1, 2, 3, 4, 5, and as many columns as the links. So we have to name the links. And we choose an orientation. This orientation, it doesn't mean that the network is directed. This is a common misunderstanding. The network is still symmetric, but then you choose this orientation to define, let's say, it's the base that you choose to define your incidence matrix. And usually it's induced by the order, by the labeling, but that's just a convention. You can define it however you want. In the framework we work on, it doesn't change anything. Then if you work with topological signals, yes, but don't worry about it. So we choose this orientation from the smaller node to the higher in number. 3, 5, 4, 5, 3, 4. And then we have link A, B, C, D, E, F, G. So this matrix, so A, B, C, D, E, F, G, takes a -1 from the node that it's leaving and a +1 from the node that is going to. It's like if we give a tail and a head to each link, and the tail is -1 and the head is 1. So link A has a -1 on 1 and a 1 on 2, and then all the rest is 0. And then same for B, 0, then has a -1 for 2, and then a 1 for 5, etc. And you can build this matrix. It's very interesting that this B, that we will see in a few minutes, has actually a topological meaning, and it's the boundary operator in topology. Also, the boundary of a one simplex is this matrix B. Okay, so now that we know what's a network and how to represent it with the adjacency matrix, let's see how diffusion works. So on continuous support, so let's say classic diffusion is modeled by Fick's law, and we have a current of the substance who's diffusing that goes with the gradient of the concentration. So you diffuse from a region with high concentration to a region from low concentration. And it's very similar on networks. So we have a networks of n nodes. And on each node, we have a substance, U. So UI, it means it's the concentration of the substance U on node I. And then if there is another, so this is node I, we consider another node J with this concentration Uj. I did it respect to I, okay. So how does the concentration on I changes if there is a link between I and J? So this concentration will be proportional to the difference of the substance on I and J. So if there is more substance in J, there will be diffusion towards I, okay? If there's less, this will be negative. So there will be substances, so the substance will flow away from you. And actually, we can put an inequality by considering a rate that is the diffusivity, the diffusion coefficient that is the same, has the same meaning. It's not exactly the same as it has on continuum support. So now if we consider the whole network, what is it gonna be? It's gonna be the sum over all nodes, but not all nodes, just the nodes that are connected. So this should be an A. It's very ugly, but it's still an A. Uj minus Ui. So this matrix is, the entries are 0 if there is no connection. If there is a connection for every node, we see what's the difference of concentration. And so we can develop a bit more. And we have J1N, J Uj. And then now we have Ui does not depend on the sum, so we can take it away. And then we have this quantity, J. This is the degree of the node. It's called Ki. And it means that it's just the number of other nodes connected to node I. So the number of incoming links. Okay, so we can rewrite the diffusion, so the variation of the concentration of the substance of the node I due to diffusion with J1N, Lij Uj, where Lij is equal to Aij minus Ki delta Ej, where delta Ej is the Kronecker delta.
So what's the significance of the I get?
Of the
The I.
is the degree, so it's the number of incoming links to node I. So all the other nodes connected to node I. So this matrix, so being symmetric, incoming or outgoing is the same. We will see, yeah, I guess next time that when a network is directed, we need to distinguish between incoming and outgoing. Okay, so this matrix is called the discrete Laplacian or Laplacian matrix, or simply Laplacian. We know it's discrete. And it's a very important matrix. And it models diffusion on discrete support. So I will just give you an intuition on what it means. And then I will go to reaction diffusion equations on networks. So if we take a very simple network, so a ring, symmetric still, of n nodes, I plus 1, I minus 1. The adjacency matrix will be a Toeplitz matrix, so 1 on the supradiagonal, subdiagonal, and then 1 here. Okay, because one node is only adjacent to the I minus 1 and I plus 1. The degree is 2 for the whole graph. So we say that the network is regular. And so L will be minus 2, 1, 1, and then 1. Okay, so the variation of a certain quantity diffusing on its graph on node I is proportional to U I plus 1 minus 2 UI plus U I minus 1. And then here we can imagine that there is the discretization that on network we always take it equal to 1, so it doesn't appear. And this is exactly the discretization of the grid, the spatial grid of a one-dimensional domain with periodic boundary condition with defined differences. Okay. The cool thing is that, so while, okay, we have a domain like this, or also a 2D lattices, it's really easy to make the discretization. But with networks, you can take any network you want with the topology, the most exotic you can think about, and then you know that still this is the Laplacian, and you can model diffusion. So while modeling diffusion on continuum, it's really difficult. You need sophisticated integration methods to understand, like finite elements. Also computationally, it's a nightmare. I wouldn't even know how to start. Here it's so easy. Okay. And then, so this, so it's easy to see the embedding of this network to this domain. But there are some networks that don't even have an embedding or a known embedding. So you can really move forward. Then, of course, you lose some things because sometimes it's an approximation. You don't have a distance between 2 points, etc. But then from the modeling point of view and computational point of view, you can do things on network that on continuous support you cannot. And so speaking of, I will leave the Laplacian. We can study reaction diffusion systems on network. And those are the equations. So again, U and V, F, UI, VI. So we have the reaction part. And now we have the diffusion, that is this one. Du, J, Lij, Uj, dV, Lij, Vj.
Do you think it'd be interesting to see what happens to the system when we allow, for example, the diffusion of the frequency to actually vary for the position?
Oh yeah, that has been done. Yes, it's something interesting. That depends when we have a. So if we go back on continuous support, we have the diffusion coefficient that are functions of space, and that's interesting. They use it also in population dynamics because sometimes you don't go where it's too crowded, so it depends on where you are. And in that case, the dispersion relation is not anymore like this. but then it's like has different zeros. It's really interesting.
I forgot to ask you last class if it was possible that it would be periodic. Would be periodic.
No, this is just the way I made the draw. I don't know. I don't know if there are cases in which can be periodic. I guess yes.
But it's very sort of standard form for this fusion. Do you assume it's Gaussian or something? The collection of Gaussian?
Usually, yes, it's the classic kernel.
Yeah.
But then I don't know much more than that. So I know that there are many many works on continuous support with regarding this. This one where I saw this dispersion relation is from a German group. I can send the paper to you after, and it's about meta population. So you have kind of mean field and network together, that you have here a well-steered system, and then you can diffuse by links. But then yeah, I have no idea if actually on network they did it. Someone did it. Okay, so the Laplacian, we know how it is, and then you'll see it many other times. Okay, so actually, yeah, I should have said more things about the Laplacian, but then, okay, this we will need it in a second. So the Laplacian, coming back to the Laplacian, we can write the matrix in compact form this way, where D is the matrix that has the degree on the diagonal. It's a diagonal matrix. And attention that in some books it's defined with a different sign. For example, the book Newman, that is an institution of network theory, uses this. When studying synchronization, they use this. We prefer this because it naturally comes from diffusion, because L, so from now on, forget this, but just be careful when you look in the literature that it might be different, because this matrix is negative semi-definite. Semi-definite, and so its largest eigenvalue is 0. So 0 is the largest eigenvalue, and all the others are negative. And it has as many zeros as connected components in the network. So the number of zeros, so let's say the kernel of the Laplacian, tells you the numbers of connected component, and it's beta 0, the Betti number 0. And it's like the continuum operator, nabla square, that it has 0 as a maximum eigenvalue, that the spectrum is continuous, but then it's the same thing. So that's why we prefer this definition. And then what else I should have said? So if the matrix is, if the network is symmetric, it has n real eigenvalues with corresponding to an orthonormal eigenvector. And then the 0 eigenvalue is associated to the homogeneous eigenvector, so the constant eigenvector. Can you guess why this is important? What do we need for Turing? The first thing that we need. We need a homogeneous stable state. So if we don't have this, and we see a case where we don't have this, it cannot work. Okay. So like this, if we take a homogeneous fixed point, we will see it in a second. We need, so if this is the constant solution, we need this to be 0. Otherwise, we cannot have Turing instability. And then, okay, we can go.
But like there you've written that the identities are identified with 0 eigenvalue.
Yeah, exactly. Yeah, it's a constant eigenvector. Although with 1, you can take any arbitrary. Yeah, actually, well, should be normalized, but yeah, it's 0. That's the important thing. And then since I defined the matrix B, L is also equal to B minus B times B transposed. And something interesting, that by changing the orientation of the links for which you define B, this doesn't change. Okay, now let's go to networks, to reaction diffusion on networks. Do I have 15 minutes? It's 2 o'clock. Okay, so I arrived to a point, and then we can, we start a bit late, yes. So then next time going back to reaction diffusion systems on networks, you can see already one very nice thing, which I already said for diffusion, but I like it even more when it's in this case, because in the end, the diffusion equation on some exotic domains, you can still solve it. But reaction diffusion equations on exotic domains, it's very difficult. And now we just have ODEs, so computational is really easy. And the geometry of the space is given by the eigenfunction of the Laplacian, which are really easy to compute. So it's really a nice simplification, I think. Because now it's ODEs because space is here, is the index of the node. So again, I will do quickly all the calculations of last time. So I will go a bit faster because we already seen it. We take a homogeneous state, so it means that on every node we have the same. So UI BI, sorry, is equal to a constant solution for every node. And then, so since the Laplacian has the homogeneous state, we don't consider diffusion. We work with the system without space. And now, system without space on network, I think it's even more interesting because system without space, it means since there is no difference in the gradient, that you don't have the links. So now you really see what it means. It's the isolated system, what in engineering is called decoupled system. And then you perturb, so you have the same Jacobian matrix as before, because the model is the same, just the space that changes, GV, sorry. And the conditions are the same, the trace negative and the determinant positive, so it's stable. Then you perturb, and you activate the links. Okay. So you can, we can linearize about so we can linearize the perturbation about the homogeneous state. And so we write now the equation for the evolution of the perturbation. So we have delta UI because it's inhomogeneous. It's a different perturbation for every node. And now with the Taylor expansion as for the case on continuous support, the delta U plus FV delta V, and then we have du sum Laplacian delta uj, and then the same GU.
So that you start with the decoupled system, and then you put in the beats that you start to do the nodes, then you perturb.
Yeah, sorry, I went probably too fast. So we have U star V star on every node. So you don't fill the links because you don't have a gradient of concentration. And then, as we did last time for continuous support, you perturb inhomogeneously. So it means that ui is equal to u star plus a delta ui. And the same for v plus delta vi, where delta u and delta v are small. And then you plug in this equation, and you have the time derivative of the homogeneous part is 0, and so you have the part with space. Here you can linearize exactly as I did last time, and the same is here. We have the homogeneous part, the sum of L is 0, and so it remains the perturbation. GV. J, L, I, J, D, J. Okay. So these systems have been studied by Ottmer in the 70s. There's the paper in the Dropbox. But then still Ottmer was, I mean, it's a great paper, revolutionary, but then still anchored to continuous support. So it's a discretization of continuous spaces. But then the modern version of Turing instability was done by Nakao and Mikhailov in a Nature Physics of 2010. I suggest you to read this paper. I think it's one of the best papers I've ever read. And they really already had the modern version of network theory, because when Ottmer wrote his paper in the 70s, still networks were not so popular, but then they are popular since the beginning of 2000s with the work of Barabashi, and Nakao and Mikhailov really revisited Turing instability with the modern theory of network. Okay, and this I should have said this before I wrote the equation, but yeah. Now we can rewrite this system in a compact form. Yeah, I will have to delete everything, so I hope you have it noted down. Because we have, for each node, we have 2 times 2 system. So it means that in total we have 2n times 2n. This is our system, 2n times 2n. And it's, I'm writing in the following way. So we have Greek Z is equal to this matrix J0 plus this matrix L, Greek Z, where Greek Z is the vector of delta U1, delta UN, delta V1, delta Vn. J0 is the matrix given by the 2 times 2 Jacobian Kronecker product with identity n, and the Kronecker products A Kronecker B, so A n times m and B S times L is A11B, A M1B, A N1B, A NMB. This is the Kronecker product. And then L is the Kronecker product between matrix D and our Laplacian, and D is the matrix du0 dv. Okay, I'll do this one last thing, and then we will start from that next time. Now, this system is a bit difficult to solve. If we remember on continuous support, the matrix that was governing the evolution of the perturbation was simply a 2 times 2, fu minus k squared du, fv, gu, gv minus k squared du. So for every wave number, we had a 2 times 2 system. So we had the modes of instability that were completely decoupled so that we could plot the dispersion relation. Okay, the great idea of Nakao and Mikhailov was, in order to study this system, I will delete everything. Is to expand the perturbation on the orthonormal basis of the eigenfunctions of the Laplacian. So the Laplacian has n eigenvalues associated to n orthonormal eigenvectors with this. So this is the equation J1n Lij for a given j component of the alpha eigenvector is equal to the corresponding eigenvalue component E. Okay. So now if we write the perturbation on this basis, so delta U E, we write it as a sum of some coefficients U alpha times the eigenvector E alpha component I, and then the same with V, some coefficients V alpha component I, and then we plug this into the linearized equation. So let me do all the steps. Sorry, 5 more minutes, but if I do it too quick, then it's so we can we have the form of the perturbation. So X is a vector delta UI delta VI. And here we have the sum of the coefficients projected on the alpha eigenvector. Yeah, here, this is just a coefficient that depends on the alpha, not on the I. We are changing bases. Now, if we write this in the linearized equation, we have, sorry. And then I really conclude. We have the time derivative of the perturbation. So the sum, sorry. Too fast. This would need a little bit more time. Okay. Then will let me know if it's clear. I maybe need to go through this again. So we had the perturbation, the derivative of the perturbation equal the linearized system. Now, instead of the perturbation, we put the perturbation written in a new basis. Okay, we are not anymore on a. So the perturbation is in a certain basis that is random because it's a random perturbation, we choose to study the evolution of the perturbation in the basis of the Laplacian. Okay. And so now we see that already, like this, we have a 2 times 2 system, because for each component we can project two times 2 Jacobian times the coefficient on the basis. And here's the magic. And now we have Fij, X alpha, Ai alpha. But we know that this, on this basis, this is the eigenvalue. So I will go above. So now this is sum over alpha, J0 X alpha, phi alpha I. And now I have again sum over alpha. I have lambda alpha, X alpha, phi I alpha.
So it's gonna be the vector of perturbation.
Yes.
X alpha. The wind that
Yeah.
I would be, and basically would be first.
Yes, exactly. And now I forgot the diffusion coefficient. So here I should have the matrix of with the 2 diffusion coefficients, but that doesn't really affect. Now we know that the basis is orthonormal, and so if we sum over alpha and over beta, phi alpha, phi beta, we have the Kronecker delta. And so all the equations starting from here, we sum over beta, phi beta. And so finally, we have that for each alpha from 1 to n, our perturbation is X alpha, J0, X alpha, plus our diffusion matrix, lambda alpha, X alpha. So now from 2n times 2n systems, we are back to n 2 times 2 system. And it's finished. This I don't know if I can delete anymore. Yeah. It lost the good part. Okay. So we can rewrite it in a compact form with Fu plus du lambda alpha, Fv, Gu, Gv plus dv lambda alpha. So this is exactly corresponds to what we saw on continuous support, where we had the minus k squared. But if you remember now, lambda is negative, it's 0 or negative. So when lambda is 0, we have no space. The first mode is the mode of the isolated system. And then all the other lambdas are negative. Okay? And so what is this? So the coefficients of the perturbative expansions, they are exactly as the perturbation in the Fourier space. They correspond to the, I think I called it ZK. So it's just a basis where it's easier, where the operator is diagonal and it's easier to study it. Okay. And so we obtain something that corresponds to the continuous case. And then we will see the dispersion relation next time, because now I'm really too late. But that's, I find it really amusing that with this perturbative expansion, we get to something that is analogous to that case. So a professor in Florence used to say that physics at the end breaks down to two things: change of basis and Taylor expansion. So yeah, that's what we did at the end Tuesday, and that's what I did today. Okay, thank you. Thank you for your patience.
Question? Let's see. No. No. So for here, no. Question? No. Second. So we can just leave. So see you on Tuesday.